past videos, we saw how you can view functions as intensional and extensional objects, and how they can be represented with just a few simple operators. And you may have asked, well, is this really true? Suppose you were designing a programming language to run a neural network. Now, the way a programming language works is it takes a function written by the user, and this might be a very complicated function, and breaks it down into a series of smaller functions. It does this by lowering the function into a format that the machine can understand. And this process is called compilation. And let's say the user writes some big, complicated function, and we want to evaluate this. Well, just looking at this syntactically, it looks like we need a lot of operators, right? We have exponentiation, we have addition, subtraction, matrix multiplication, division, and then this square root operator. Well, it turns out that you can express a lot of these operators in terms of a composition of simpler functions. So for starters, if we have an exponent, then this is just the base times itself, k times. And what's a product but repeated addition? And you can take this one step further to just get a single operator, but that's a topic for another video. So this process is one possible lowering for scalars, and it turns out that most machines implement this operator already, so if we can lower onto it, then we can evaluate. Now what about matrices? Well, if we have some matrix, m raised to the k, then this is just repeated matrix multiplication. And what is matrix multiplication? If we have two matrices, M and N, well, this is just a matrix whose elements are just the product of vectors. And what's a vector product? Well, this is just the sum of the individual elements. And we already know how to lower this operator onto multiplication and addition. Now you might be wondering, well, what about inverse operators, right? We covered exponentiation, multiplication, and addition. What about their inverses, right? So we have logarithms, division, and subtraction. For matrices, sometimes there's an inverse and sometimes there's not. But for vectors, well, we're out of luck. So in general, it turns out that many functions we can represent using these operators have no closed form inverse. So then how do we evaluate the square root function? One algorithm for doing this is based on gradient descent. So if we have a random input, our initial guess, we can take the output, call it y hat, and compare it with our target. And if y hat is less than y, then we follow the gradient uphill. Or if y hat is greater than y, then we follow the gradient downhill. And eventually, it can be shown that if this function, call it f, is always increasing, as it is the case with exponentiation and root, then this process of gradient descent will converge to the inverse. Now, you probably don't want to run this for every input, so you can build a lookup table. In fact, this same method can be used to sample from a probability distribution, and we'll see that in another video. So to sum this up, if you're implementing a programming language, there are really just two operators you need. And these two operators, addition and multiplication, can give you a lot of expressivity. we saw that by lowering compound expressions onto these operators, that we can compile a large class of elementary functions, and this includes many neural networks, probability distributions, and other differentiable programs, into an intermediate representation, or IR, which can then be evaluated by an interpreter or virtual machine. And by doing this lowering carefully, then the interpreter doesn't need to know anything about our high-level functions. Not only is this intermediate representation much simpler to optimize, but it also allows us to implement transformations, such as the gradient, in this much simpler language, the intermediate representation, without needing to reason about transformations in this much more complex space of functions. So this process reduces complexity, but not expressivity.